So, I am going to start with another equation, which is the idea is very similar to what we did for hydrodynamics. Okay. So, now we go to another phenomena. Okay. It's called surface growth. I am going to explain what is surface growth. And there is very famous equation. In fact, this equation called KPZ equation, Kardar Parisi Zhang, and that equation has huge following, okay, in statistical physics. This is more famous in statistical physics compared to Navier-Stokes. Navier-Stokes, they do not work with that, but they work with KPZ. So, for completeness, I thought we should look at KPZ, but there are similarities. So, I am going to show you the similarities, but the approach which is used here is with they use noise, and it's similar to 5-4 theory for Wilson. So, you will see that. So, I think you should be able to at least connect what is done where. Okay. So, 5-4 theory you will see lot of similarities, and with noise. Okay. It is a dynamical thing. So, there are certain changes which is done here, and we should see the difference. Okay. So, I took it from this book Barabashi and Stanley. It is a famous book. Okay, one more request, everybody please fill up the form and tell your friends to fill up the form. I need the feedback. This course is very different, and be honest. Okay, you do not abuse me, but you can write your comment. I mean, you can write your comment harshly or softly. Okay, so please do write. You want to write comment after your grade is submitted? I would like I like some comments. Okay, so I can tell you when I submit my grade, then you can send your comment. Just write some whether you are. It is a difficult course, but I hope it is useful and very at least fascinating. That is what I would. Okay. So, shall we? All right. So, we will do another phenomena. So, I worked basically with turbulence so far, but there is one very famous equation called KPZ equation. Okay. And there are a lot of work in this equation, and the field theory for KPZ is well, it is on the same lines, but it is not self consistent. It is with noise, and is extension of Wilson 5-4 theory. So, if you please recall Wilson 5-4 theory, which was non-equilibrium theory, no frequency, no time, but now it is extended to equilibrium theory, non-equilibrium theory, and so we will see that KPZ. I want to do it today, so let us get there in 15-20 minutes. So, but I need to set up the framework. Okay. So, surface growth phenomena. So, this became very popular in 1990s. Okay. Though the phenomena is I think very common. So, if you put a blotting paper in ink, so the ink so this is a blotting paper and ink is flowing up, right. So, you can see that there is a profile when you look something like that. So, and if you wait for longer time, then this surface will keep going up, right. So, this is called surface growth, surface growing, but this is for fun, right. I mean, this is not really of practical use. But we can do real stuff by making chips, right. So, how do you, so there is a deposition of silicon or deposition of material on top of surface, okay. And this used, I mean, one surface you drop gold particles. So, there are a lot of material science connected with surface growth. So, it is a very practical problem, and so people try to make theory out of it. Okay. So, there is some successful theory. Of course, theory does not really match exactly with experiments, but there are certain overall picture we get from simple equations. Okay. So, this picture is again from this book. So, my discussion right now is basically from this book Barabashi and Stanley, and I have taken quite a bit of material from this book. So, So, surface is growing, no, I mean that this blotting paper, the ink is going up. So, it turns out we look at this roughness, this called roughness, W is called roughness, and H is a height variable. So, this is x axis, and for every x I have height of the ink column, right. So, this is certain profile. So, H is function of x and time. Okay. So, now or here it is I is in x variable. So, normally people also write in discrete variables. So, I is the site. So, h minus average height at given time. So, take this h of x t minus h at time t. Height is changing with time. So, I subtract. So, this will be, if I take the average I will get 0 at a given time, right. By definition the h of t is the average of h x t. But if I take the square of this, then I will get non-zero value if I average. So, take the square and then take a square root and divide by length of the system. So, this is average RMS value of height at a given time and given time. Okay. So, this function of L, well, depends on system size as well and depends on T. Okay. So, this is called roughness. Okay. Now, this is plotted for a generic is a theoretical plot, but we find that in experiments too. So, this roughness is increasing with time is a power law. Okay. Is a time is x axis. So, this in fact goes as t to the power beta. Okay. Beta is exponent and that depends on how you model it. Okay. And then it finally becomes flat. So, roughness, by the way, the height is increasing, but finally the roughness does not change with time. Okay. So, it will fluctuating going up, but this roughness, this object flattens. Okay. And this turnover, I mean the change of behavior occurs at certain time t is called T x. So, from this picture we can see that this in the early phase it is 2 to the power beta, beta is an exponent, and this level, the saturation level depends on L. So, W of L saturation is L to the power alpha, alpha is also an exponent. Now, we have two exponents alpha and beta, but it turns out I can combine these two relations using same idea as Widom scaling. I did in the class, this Widom scaling I did earlier. Okay. So, this Widom scaling I can combine in the same manner. So, the idea is that I write single function for roughness which is L to the power alpha, but then there is a non-dimensional variable t by L to the power z and is some function of that. Okay. And now we got a new variable called z, and what is this z? So, we can get this z by the following. Okay. So, I write this as t to the power beta, no, the at early time or in the early phase t to the power beta. So, now from this relation, now t and L are related. Okay. So, these two variables are related. So, I write t as L to the power z. Okay. So, if I take two systems, they increase the system size by factor 2, then the time will also be increasing for reaching that particular roughness, but this will not be factor 2, but it will be some function of z. You understand what it means? So, for given L I get this, okay, but if I increase L, then my what happens if I double it, then how will the curve look like? Okay. So, then the curve may look like that. Okay. So, what is the factor? So, this is the relation for given time t, these are the two different values for different L's. Okay. So, now I can rewrite this, well, I mean from this you can see I write this t to the power beta, but t is L to the power z, right. So, it is L to the power z beta. Okay. Z beta must be equal to alpha, because my alpha is the exponent for L. So, we get the relation Z equal to Z beta equal to alpha. Well, I am just using this relation, okay, to replace T by L. So, Z equal to alpha by beta. Okay. So, this is another exponent is called in fact dynamical exponent. Okay. So, let me just write that this is very important relation. How does the frequency scale with wave number? So, you see 1 by time will be frequency and 1 by L will be wave number. Okay. So, that goes as Z. Now, we know for hydrodynamic turbulence what is Z. So, frequency has dimension of nu k squared, nu k squared. This is a renormalized viscosity. So, what is nu k? Is k minus 4/3, right? I derived that k squared. So, this k 2/3, which is k was Z. So, Z is 2/3 for turbulence, hydrodynamic turbulence. Okay. So, this Z is a very important exponent for all dynamical phenomena, which connects frequency with wave number or time with L. Okay. Of course, this is I am deriving it for surface growth, but this relation we already derived it for hydrodynamic turbulence.